Welcome back to Mass Transfer Operations 2 course. We were discussing on liquid extraction. Now, we will be discussing on the effect of temperature on liquid equilibria and design calculation of single stage extraction. So, the first thing that we will be discussing on the effect of temperature on liquid equilibria, that the effect of temperature is very strong actually in this liquid equilibria. The miscibility of liquid pair generally increases with temperature, and miscibility of suppose BC pair increases more rapidly than AB pair in the type 2 system. So, let us take this the system 1, that is we can say this one the first system, that is equivalent to, we can say it is equivalent to T2, this one, where we can say we have this binodal type system, where we can say this extract arm and this is a extract arm and this is raffinate arm, both are present here. And say whenever we will increase the temperature from T2, suppose this is actually this T2, say 25 degree Celsius. Whenever we will be increasing the temperature from T2 to say we can say this T1, say this, that time what will happen, the binodal part actually will contract, and then say we will be getting one point here, this is equivalent to, we can say this point. So, this temperature, corresponding temperature, we can say this one will be say like T is equal to say 34.5 degree Celsius. So, this is 34.5 degree Celsius, where we can say it will touch this BC line. So, this in BC line it has touched here. So, with this BC arm, and if we further increase the temperature, so we can say this one again it will be contracting more and it will be entering like this. So, we can say this one, this situation 3 is nothing but this one. So, this we can say this one, this is like T1 temperature. Okay. And say if we go on increasing the temperature, so what will happen, this plate point actually will be, so we can say contract, and ultimately it will come to this line, AB line, like this, say in this AB line it will be touching that point. So, at the critical solution temperature, where we can say this one the binary plot actually will be touching this AB arm, we can say this one, then we can say type 2 system will be converting into type 1, and that particular temperature is called critical solution temperature. So, we can say this one, the two phase region of this equilibrium diagram for type 2 system will contract, and we can say this one with increasing the temperature and eventually vanishes at the temperature called critical solution temperature. So, we can say this one will be getting one point where this binary phase actually will be vanishing, and that temperature is called critical solution temperature. So, the critical solution temperature is the minimum temperature at which we can say component A, B and C of a type 1 system becomes miscible in all proportions. So, it will be converting into, we can say this one, the first type of this liquid equilibria, where we can say this all A, B, C are miscible in all proportions. So, that point we can say this one, that temperature is called critical solution temperature. Now, that another important topic in this liquid extraction is the solvent selection, because the selection of the solvent is most crucial, because you see once the extraction process is over, then whatever the exhaust solvent will be there, that we can say this one can be used for the other process, and whatever the extract actually will be getting extract phase, from there also after separating that target component, we need to purify that extracting solvent, and that will be used for the next cycle. So, the right solvent is the key for the successful separation by in the solvent extraction process. So, solvents are mostly organic. The important criteria for solvent selection are few, like we can say selectivity. First important key point is the selectivity. So, selectivity or we can say this preferential uptake of the solute by solvent over the carrier is most important factor. So, that selectivity is beta, we can say this one C A is equal to Y C by Y A by X C by X A, where Y C is we can say this one weight fraction of the C in extract, where Y A is the weight fraction of A in the extract and X C is the we can say this weight fraction of C in raffinate and X A is weight fraction of A in raffinate. And say this one whenever we will be reaching this plate point, there this beta will become is equal to 1, because at plate point say Y A will be equal to Y B, this Y B is equal to X A, and also X C is equal to Y C. Because if we remember this plate point in any of the say triangular diagram, maybe right angle or equilateral triangular diagram, we will find that say this one plate point is the common point of both extract arm and the raffinate arm. So, there we can say this Y A is equal to X A and X C is equal to Y C, or we can say this one solute concentration in both the phases extract as well as the raffinate is same. So, whenever it will be 1 means it has reached the plate point. So, our target will be to get this beta value more than 1. So, that selectivity or we can say this one separation will take place. Okay. The second criteria, that is we can say this one carrier solvent immiscibility. So, if the mutual solubility of the carrier and the solvent, we can say this one is very low, they can be satisfactorily separated in the settler. But if there is we can say this one miscibility is there with this A and B, then we can say this one once the solute actually will be transferring from A to B, but you see after that we will not be able to separate the solute C from both the phases, because the both A and B we can say carrier solvent as well as the extracting solvent both are now miscible. So, that is only small quantity of the solvent will be retained in the raffinate and small quantity of the carrier will remain dissolved in the solvent. So, cost of further separation of the phases by distillation or otherwise it will be very small. And the third point is this we can say interfacial tension. The interfacial tension between carrier solvent and the extracting solvent has two opposite effects, and at low interfacial tension that we can say this one it favors this fine dispersion of the one liquid in the other, thereby increasing the specific interfacial area of the mass transfer. So, we can that is good. The coalitions of the droplet leading to the separation of the raffinate and the extract phases does not occur rapidly or readily if the interfacial tension is low. So, we can say this one there is a mixed reaction for the interfacial tension. So, low interfacial tension or high interfacial tension both are we can say this one sometimes beneficial, sometimes they have this adverse effect also. Whenever we will be talking about the density, the driving force for the phase separation in the settler actually is the difference in the densities of the two phases, because you see once the extraction process is over, we need to wait for a long period of time to separate the carrier phase and the extract phase this one in the settler. So, the density of lighter phase should be at least 5% less than that of the heavier phase in order to ensure the smooth phase separation. Otherwise, these will be remain in the miscible system and we will not be able to separate those very easily. And the another important factors are like viscosity, vapor pressure and freezing point. So, this should be very low for ease in handling and storage. And another point is this chemical reactivity. The solvent should be inert and chemically stable, otherwise it will this extracting solvent may be reacting with this target component or solute, and then we may not be able to separate this solute from the extracting solvent also. And the another important this point is this recoverability, means it is always necessary to recover the solvent for reuse and must be done by another mass transfer operation like distillation ityadi etc. So, solvent should not form actually form azeotrope with the extracted solute. So, that must be taken care of. So, before selecting one extracting solvent for the extraction process. Then distribution coefficient, we can say this one y star by x, that is at equilibrium must be greater than 1 or large value, that are desirable since less solvent will be required for the extraction. Otherwise, we need to get we need to use huge amount of the solvent for the separation of a particular, you can say this extent, and then the solvent should be non toxic, then non flammable and low cost. We need to remember this one whenever we will be selecting the suitable solvent for the extraction purpose. And the accumulation of the impurities, that is also another point. The accumulation of impurities is observed if the solvent is of low volatility. So, it lowers this interfacial tension and surface resistance actually to allow mass transfer between two phases. So, at the end we can say this one, hardly any solvent will satisfactorily meet all the above criteria. Choosing a solvent is again a matter of striking a balance between properties and cost of the solvent and equipment and operating costs and ease of operation of the other. So, selection of the solvent actually is really a tough job for the extraction process. Now, we will be discussing about the equipment and flow sheeting. So, in extraction process there are two different types of operations. One is the single stage contact operation, another is the differential or continuous contact operation. In single stage operation, we will be discussing these two different types of extraction processes. One is this single stage operation and another is the multi stage cross current extraction process. So, we will be discussing about the single stage extraction process. So, let us start with this one stage like this. We will start with this flow sheet diagram. Let us take say this one stage 1. So, we have the solvent, extracting solvent, we can say this one say S, and the concentration of the solute is Y s in the extracting solvent, and also we have this feed in the beginning. Say we have this suppose feed with the solute concentration as X f. Now, we have this in the extractor, we have this mixer settler. Say once it is extracted, say then we have two different phases like this. One we say that is our target, that is we can say this one extract phase, that is we can say this one E 1 with this solute concentration like this Y 1, and one is this we can say this one raffinate, that is we can say this one with the solute concentration is X 1. So, we can say this one is the extracting solvent, this is feed, this is we can say this is raffinate, and this is extract. So, if we do the material balance, so we will be doing this one very simple material balance we will be doing. F plus S 1 is equal to we can say this one E 1 plus R 1, that is nothing but we can say this one same M 1. Like this is we can say this one whatever the mixture we have. Okay. And if we do the solute balance, because our target is to separate the solute preferentially from feed to extract. So, if we do this one, that will be say in terms of solute concentration F X f plus S 1 into Y s, that will be is equal to E 1 into Y 1 plus R 1 into X 1 is nothing but we can say this one M 1 into X M 1. So, that X M 1 we can say this one mixture is the we can say this one mass of the summation of feed and extracting solvent or raffinate plus extract, but this X M 1 we can say this one, this is we can say the one fictitious solute concentration that we call say if it is not separated, but the solute concentration in the mixture. Okay. So, this xm1 we can say this one will be, that is the solute concentration in the mixture will be nothing but we can say this one, if we take this left hand side say f xf plus S1 into Ys divided by, so we will be taking one like M1 is nothing but we can say this one M1 is equal to say F plus S1, or we can say this one again we can say this F xf plus S1 into Ys is nothing but we can say this one F in plus S1 into, just like we can say this is a mixture into xm1. So, from here we can say this one say F by S1 will be nothing but we can say this one x m1 minus y1 divided by xf minus xm1. So, that also we can get this one, just we can say this one f by S1 also will be getting from here in terms of, so we can see the xm1, y1 and xf. Okay. And again we can say E1 into Y1 like this, if we say we will be trying to get E1 by R1 or E1 by M1, if we want to get like this E1 into Y1 plus R1 into X1 is equal to M1 into XM1 is equal to, we can say this one E1 plus R1 into xm1. Just in place of this m1 we are putting this xm1, and like we can say this one, if we just manipulate this one we will be getting this one u1 into say y1 minus xm1 is equal to, we can say this one r1 into xm1 minus x1. So, from here we can say this one we will be getting E1 by R1 is equal to say xm1 minus x1 divided by y1 minus xm1. Okay. So, similarly, for E1 by say m1 we will be getting xm1 minus x1 divided by y1 minus x1. So, we will be getting all these. So, we can say this one say this equation like this, it is indicating that the point M or say we can say this one point M1, that is we can say this one lies on this point. Suppose we have this feed point and we have this suppose S1 point here, and if we add this feed and S1 and this somewhere we will be getting M1, that is we can say this one mixture point, that will be lies in between F and S1, and if we draw the tie line, this whatever the we can say this one binary phase actually is there in this diagram, it will be touching this raffinate arm at R1 and extract arm at E1. Okay. Now, it has touched this raffinate arm at D point. So, this is we can say this one raffinate arm, and this suppose this is the plate point. So, and this is extract arm. So, we can say this one whenever this F and S1 touches this raffinate arm in point D. So, we can say this one that minimum amount of the solvent, we can say this one from here we will be getting minimum solvent, minimum solvent requirement, actually we can say this one for this particular separation, and from the G we can say this one corresponding G we will be getting what will be the extract actually for this minimum solvent flow rate, what amount of the extract actually will be getting, and maximum amount of we can say this one extract will be getting this one from we can say this one from this point K. that is we can say this one maximum extract, we can say this one that will be getting from K, that is we can say this one maximum extract. Maximum extract will be getting from point K. Okay. And point L actually represents the we can say the raffinate with the lowest possible solute. So, we can say this one raffinate with lowest possible solute. Okay. So, these are the we can say this one we can say these expressions from the we can say this ternary diagram. Okay. We will be now discussing about the single stage extraction, how to plot all these actually in the right angular triangular diagram. Also we will be doing this on same thing like this, whatever we have plotted in the equilateral triangular diagram, like we can say this one in the right angular triangular diagram, we have this feed point here and we have this S1 somewhere here. So, we will be now adding this also and adding this F and S1, and we have this XM1 from this XC diagram, that is we can say this one, that is XM1. Okay. So, from this XM1 whenever we will be drawing one tie line, we will be getting this E1 and R1. So, or we can say this one, whenever we have this particular feed and we have this extracting solvent, if we add these two and if we allow this for a long period of time, it will be separated into R1 into E1. Okay. And say this one just like here also, whenever we will be getting this G, that we can say is minimum amount of the extract, and corresponding this point actually is called minimum amount of the solvent requirement, and this L we can say this one, where this minimum amount of the solute C, this we can say this one X, what about X C, that is the minimum amount will be there in the raffinate. We cannot extract more from there, or we need to increase the solvent, huge amount of the solvent to extract from here, because you see if we want to go down from here to like this below line, then our solvent requirement actually will be high. So, K point actually indicates that the maximum amount of the solvent required to get the maximum extraction. Here we can say the G is the minimum amount of the extracting solvent required to get this amount of the extraction like this. Okay. And now, we will be doing the we can say this one the step by step graphical procedure for the we can say this one calculation in the single stage extraction unit. Okay. Now, we need to do one thing. Firstly, the first point will be we need to draw the ternary equilibrium curve on the equilateral triangular diagram, or we can say any right angle triangular diagram like this. So, we need to draw ternary diagram that is we can see this one equilibrium curve. Maybe in any system like this, we can say this one maybe right angular or equilateral triangular diagram. Now, we need to locate F and S1. Okay. Then the second step will be we need to calculate XM1. So, we have this equation like this XM1, we have this equation, from there we will be calculating this, and then we have to locate point M. Inside this we can say this one two phase region. Okay. That will be we can say this one, it will be like this in between in the FS1 line. Okay. Then we need to draw the tie line E1 R1 through this point M1 M or M1, we can say this one. If we take this one for first system, that is M1. Okay. So, from there actually say in the raffinate arm we will be getting R1 and in the extract arm we will be getting E1. From the terminal actually we will be getting from the terminals we will be getting the solute concentrations x1 and y1 will be getting. Will be obtained. Okay. And now we will be getting this one. We know this equation like this. We say F plus S1, that is solute balance is equal to, we can say this one M1 is equal to E1 plus R1, and in terms of solute concentration this F xf plus S1 into say Y1 is equal to M x M1 is equal to say E1 Y1 plus say R1 X1. From there actually we can say this one E1 by say R1 will be equal to say X M1 minus X1 by Y1 minus X M1. So, we will be getting this one. So, if we have this, we can say this one the two terminals in the extract and raffinate arms. If we have like this equilateral triangular diagram, let us take say this is the equilibrium line, say this one equilibrium line. So, this is we can say plate point, suppose this is the feed point location and this is the say somewhere here it is say S1. Now, first step is like this, we need to draw this F S1 and then we have somewhere we can say this one M1 we have identified by this calculation. Say from this we can say this one we need to draw, suppose this is the tie line. So, where we can say this one, this will be say this will be R1, this will be say E1. Okay. So, from R1 we will be getting say R1 will be getting Y1 and from this extract we will be getting X1. Okay. So, from this point actually we will be getting both X and Y. Okay. And then say let us required percentage of the separation of solute is specified. Suppose the required percentage separation of solute is specified. So, then we can say this one, we can get the necessary solvent flow rate also we can calculate. So, for that case actually what we have to do? We have to calculate R1. So, step will be like this, we have to calculate R1 and then from the graph we will be getting X1. As X1 is known, suppose X1 is known. So, we can say this one Y is calculated from equilibrium plot, Y1 is calculated from say equilibrium plot and then E1 actually will be expressed in terms of S1, will be expressed in terms of S1, as we can say this one E1 is equal to F plus S1 minus R1, just from the material balance actually we will be getting. So, this will actually involve the trial and error method. Okay. Now, we will be solving one problem. From there actually we will be able to this one we can clarify the steps. This is your right angular triangular plot. Here also we can say, suppose we will be taking this feed point here and S1 somewhere here, like this we will be adding these 2 points. Then we have this say x m1, and from there we will be getting this we can say this one r1 and e1. From there we will be getting x1 means say this one y1, and from there actually we will be getting the composition of the solute in the extract and raffinate, and from there we will be getting what will be the solvent flow rate. If we want to get minimum solvent flow rate also, that we will be getting from here, say from this point we will be getting whatever the minimum solvent flow rate required for this one extracting solvent, how much amount of suppose E minimum actually is required, that we will be getting from here. Now, if we say want to get that say suppose the solvent flow rate is given, suppose required extraction is specified. So, let us take 90% extraction is required, then what to do like this. So, we need to do this one, we have to calculate this R1, and from there we will be getting this x1 as x1 known, then we will be getting what will be the E1 like this. So, from there also or from the graphically also we will be able to solve this one. If we solve one problem, then I think we will be clarifying those. So, the problem is like this, 1000 kg of an aqueous solution containing 50% acetone is contacted with 800 kg of the chlorobenzene containing 0.5 mass percent acetone in a mixture settler, followed by separation in the extract and the raffinate phases. So, this is we can say the single stage operation. There we have this say feed is there 1000 kg and solvent is 800 kg. You note that the solvent extracting solvent is not the pure solvent, means it contains a small amount of the acetone, because it may be obtained from the previous extraction process, that is why 0.5 mass percent acetone is already available there. And determine the composition of the extract and the raffinate phase and the fraction of the acetone extracted, how much acetone actually is extracted. And next one is that they calculate the amount of solvent required if 90% of the acetone is to be removed from this feed. Equilibrium and tie line data are given like this one. Say whatever the data points are actually presented here, these are all say x c and y c values, say these x c and y c values are in equilibrium. So, these are we can say this one equilibrium data points, and one point is that here whenever we will be calculating the total amount of the acetone, then we need to get that suppose from feed out of this 1000 kg 500 kg acetone is there, but whenever we have this 800 kg the solvent chlorobenzene, there also 800 into 0.5 mass percent, that amount of acetone also will be coming to the system, because you see whenever it will be mixed and say this one settled, there that acetone also will be contributing towards this recovery, but whenever we will be doing the recovery calculation, we need to subtract that acetone which is carried by this extracting solvent. Okay. So, like this we will be solving this one. For that we will be doing like this, whatever the values are already given like this, we can say this one we will write first those. Say given values are like this. Say feed is 1000 kg, then mass of the solvent, say we can say this one S1 is equal to say 800 kg, and we know that say this M1 is equal to A plus S1. So, that is nothing but we can say this 1000 kg plus 800 kg. So, that is nothing but 1800 kg. Okay. And this x m1 actually will be like this, just using this formula F x f plus S1 into y1 divided by say F plus S1, that is nothing but we can say this one F means 1000 into 0.5 plus 800 into 0.005 0.5% divided by 1800. So, it is coming out as 0.28. So, in this we can say this graph. So, whatever the we have drawn this here, actually we can say in this graph, suppose say this one the variation of this x c and y c with this x p and y b. Suppose say we have this equilibrium plot here, and now we have this x m 1 is equal to 0.28. Say somewhere we can say this one, it will be like somewhere else. X m 1 actually we have got, but so we will be getting say x m 1 in some places like this, that is 0.28, and we know that feed point is nothing but we can say this one f, say this is x b will be equal to we can say this one for this feed x b, that is 0, and because in the feed there is no chlorobenzene, and this x c that will be like this 0.5. So, somewhere it is 0.5 like this, this is the feed point. So, we can say this is the feed point, and the solvent one, that is we can say this one x p or y b whatever may be the for solvent one, that is we can say this one 0.995, because 0.5% is there as a solute, and y c is 0.005. Okay. So, x b is equal to this one and y c is equal to 0.005. So, it will be coming like somewhere else here. So, that is we can say this one S 1. Now, we can say this one we will be drawing the we can say this one straight line from F to S 1, then we can say this one somewhere we can say this one will be getting this point mixture actually. So, that will be somewhere else, this one we can say this one M 1. Okay. Now, from this figure we can say this one solid constant. Now, we will be getting this whatever the tie line value is there, say will be like this. So, suppose tie line value from this supplied data we will be getting says what is called this R 1 and E 1 we will be getting this one. So, from this tie line value say so whenever we will be plotting this one from this tie line value, say we will be getting this whatever the we can say x c and y c means x 1, here we can say this one whatever the x 1 value is and whatever y 1 value is there we will be getting this one. So, from this we can say graph paper, say x 1 actually is x 1 is 0.236 and y 1 is 0.302. So, that is nothing but, so we can say this one whatever the tie line value, this is not the tie line actually, say will be like this one 0.236 and this one. So, okay. So, this one actually this we can say this R 1 and this one is E 1. We need to get this one, the exact value actually we will be getting from there whatever the equilibrium data points are there, like for x 1 and y 1 will be getting like this, and we know this one that E 1 plus R 1 that is nothing but we can see this mixture one, that is 1800. Okay. And we know this x 1 and y 1, just if we do this calculation in the graph paper we will be getting this one. I have not drawn the correct tie line data, that is why initially it was showing something different value, and from there actually we will be getting say E 1 is equal to we will be getting say we can say 1200 kg and R 1 will be the rest of this one from 1800, that is we can say 600 kg. Okay. So, we can say this one how much mass actually we can say this one of the acetone leaving with the extract. So, we can this one mass of acetone, that is we can say this one solute actually acetone leaving with extract is equal to we can say this one E 1 into y 1, that is we can say this one E 1 is say 1200 into Y 1 is equal to 0.302. So, that is we can say this one is equal to 362.4 kg. We know that the amount of acetone that was present in the feed, that was say we can say this one mass of acetone in feed, that is equal to say 1000 into 50% kg. So, it is 500 kg. So, we can say this one, and the amount of acetone, I told that this solvent, extracting solvent also contains some amount of the acetone also. Acetone entering with extracting solvent is equal to we can say this one S 1 into Y 1, that is 800 kg into 0.005. Okay. So, that is equal to 4 kg. So, total we can say this one total maybe 504 kg acetone was there in the system, or we can say this one whatever the total extract is there 362.4 kg, out of there 4 kg is contributing from extracting solvent itself. So, we can say this one net amount of we can say this one net amount of acetone, we can say this one extracted is equal to we can say this one 362.4 minus 4 kg. So, that is equal to we can say this one 358.6 kg. This is 358.4 kg. Okay. So, we can say this one fraction of acetone removed by extraction, that is we can say this one 358.4 divided by 500 into 100, that is we can say equal to 71.68%. So, this is we can say this one this extraction efficiency 71.68%, or we can say this one if we say how much fraction 0.7168 fraction of the acetone that was present in the feed is extracted by this process, means using this 800 kg solvent with 0.5% acetone, this 358.4 kg acetone is removed. Okay. The next question actually is that say if we can say this one 95% acetone from the feed actually is to be removed, then what will be the amount of solute, the what amount of solvent actually will be requiring, that will be getting like this. So, for that case we can say this one that if 90% say we can say this one, if 90% acetone removal is required, So, then so we need to do this one. Now, we are assuming that mutual solubility of water and chlorobenzene actually is negligible. So, it is not say both the solvent A and B are not mixing, this one we can say this one we are neglecting that part, and we can say this one we need to do the we can say this one we can say that the raffinate phase is free of water. Whatever R 1 is there, that is we can say this one only chlorobenzene is there, that is we are assuming, but in reality it may not be the true case, means this one whatever the chlorobenzene is there, it may contain some amount of the water. So, we can say this one whatever the R 1 in the beginning we need to find whatever the this R1, like this we can say this one 50 plus 500 kg. So, that is we can say this one 550 kg. Okay. And say we can say this one, there actually this x1 will be, we can say, means a solute concentration in the raffinate will be 50 by 550. So, that is coming out to be 0.091. Okay. And this one y1 actually will be, so we can say this one, say from this figure. So, if we have x1 is equal to say 0.091. So, this y1 will be equal to, we can say this one like if we say here somewhere here actually it will be 0.091, like somewhere here. If we come here, if we can come here like this, it will be like this, means corresponding y1 value will be like this, from the we can say this equilibrium value, that will be like this point, that is 0.105. So, we will be taking this one, that x1 will be like this, that is y1 will be here 0.105. So, now we will be getting that, I told that say this one E1 actually will be getting like this 1000, that is we can say this one feed minus S1 minus this whatever the R1 we have, this 550. Okay. And so that is we can say this one, we are getting this one is equal to 450 minus S1. So, U1 is equal to this one, and just by doing the material balance we can say this one F XF plus S1 Y1 is equal to, we can say this one E1 Y1 plus R1 X1. Okay. So, this 1000 into 0.5 plus S1 we need to find out, into S1 will be like this 0.005, and that is already given in the problem, is equal to, we can say this one E1 is equal to 450 minus S1 into Y1 is equal to 0.105 plus R1 is equal to say 550 into X1 is equal to 0.091. Okay. So, from here actually we will be getting like this, S1 is equal to 4027.5 kg. So, we can say this one, if we want to get 90% removal, acetone removal, so we need, we can say this 4027.5 kg acetone. Okay, the chlorobenzene, we can see this one solvent. So, you see using 800 kg solvent, we were able to separate around say 71% solute, and for this 71% to 90%, we had to this say from 71.68%, we had to spend 800 kg extracting solvent. From 72% to 90%, we had to spend huge amount of the this one what is called extracting solvent. So, we can say this one at the end, or also we can say this one whenever we will be coming to this zone, we say we need more amount of the extracting solvent to separate the remaining amount of the solute from the this one feed. Okay. Now, say we will be doing this one, this construction of conjugate line. So, using this tie line data, that is also one important this one what is called calculation. Say in some cases we can say this one we have very few tie line data. So, in that case how we can get the, we can say this one x1 and r1, or we can say this one E1 and R1, we can say this one how much amount of extract and raffinate will be this one obtained. So, we will be getting this one using this conjugate line. So, that is done very easily. Suppose the this horizontal axis from A to B, this is x b and we can say y b, and this is, you can see this one x c and y c. We know this is the plate point. Okay. And say we have two tie line values like this tie line we have and this tie line we have. From there how will be getting this conjugate line? Once we are able to get these two tie lines at least, then we will be able to get the conjugate line. So, what we will be doing? Say from this raffinate point, this one what is called this lower raffinate point, we will be drawing on a horizontal line, and from this extract point we will be drawing this vertical line. Where it will be meeting? Let us take this point K. So, accordingly, so from this another extra raffinate arm, suppose this from this tie line we will be drawing another vertical line, and from this raffinate point and from the extract point we will be drawing one vertical line, so perpendicular line. So, whenever it will be touching this one, let us take one K1 point. We have this plate point, and if we draw this plate point and all this, we can say this one common point actually say K1, K and then S1 or S. If we draw this line, so we can say now we have this conjugate line. If we have this conjugate line, so if we want to get any other say tie line values, so we know that in plate point say the both the x c and y c are same. And if we take, let us take any other example, say if we want to get the some point here where actually we want to get the what will be the extract and raffinate point for this mixture. Let us take say this one, this point where the tie line, what is the tie line value. So, we will be doing one thing from here actually we will be drawing the, we can say vertical the perpendicular line, and it is, we can say this one we will be drawing this vertical line from here, and now we have this point and this point we will be adding this. So, that will be one E1 value, that is corresponding will be R1 value. So, we will be able to get the, if we have this mixture also, so we can say from there it is not actually really the mixture. Say if we want to get some, we can say this one extract and raffinate point from this we can say conjugate line, we will need to follow this one. Or if we have this mixture, then it is very easy to get this one from the mixture point, we will be able to get this, we can say conjugate line also, we will be able to get this extract and raffinate this one point as well as this composition. Okay. So, thank you very much. In the next class actually we will be doing this design calculation for multi-stage extraction.